What we're going to look at now is the behavior that occurs between volume of a gas and absolute temperature. Okay, and so when if you have a gas volume and you confine that gas to a container that won't let any more in or out, if you hold that gas at a specific temperature, then these variables actually change in the same direction. Yesterday, when we increased the volume, the pressure went down, and when we decreased the volume, the pressure went up. So that was an inverse relationship. When you have a gas, if you increase the temperature, the gas expands. So the volume increases. Okay? If you have a gas and you, sort of a leaning tower of T here, if the temperature goes down, then the volume's also going to go down.
Just like water, right? Like when water freezes.
Yeah, well, water actually expands when it freezes, but that's a whole different thing.
Oh, yeah.
But gases, if you take a balloon, you blow up a balloon, tie it off like we did when we were doing balloon models, put it in your freezer. When you open up your freezer, that balloon's going to be smaller because as the temperature went down, the volume went down. Okay, try it sometime. See if I'm not telling the truth. Okay, now once you take it out of the freezer, it's going to blow back up in a hurry because the gas will heat up in a hurry too. You can actually sit there and watch the balloon get bigger as the temperature of the gas inside gets larger, higher. Yes.
How did oceans form?
How did what form? Wow, that's a really big question. I just
take some time to answer that one.
Yeah, I mean, you're talking about a lot of geological history to go through how that happens. There's a lot of debate about how they form, about whether the water was already present on the Earth and evolved to the surface, or whether it came here in the form of comets, mini comets, things like that, or maybe a little bit of both. But it's kind of an open question, really. And we're talking about, I don't know, 5 billion years ago. I wasn't around then. Believe it or not.
But that means volume that's a V and a T, right?
Yes. So if the temperature goes down, the volume is going to go down. And also, this is true. If we took those syringes we were using in the lab yesterday, and we were to insulate that syringe so the temperature of the gas can't equilibrate with the surroundings, okay, it can't warm up because the outside's warmed up or not, and we were to squeeze the gas down, the temperature would go up. Okay, we can make the temperature increase by squeezing that gas down. We can make the temperature go down by letting the gas out. Yeah, just give me a chance to write a pass, okay? One way you can get things to cool down is to take a gas and compress it and let that temperature equilibrate, and then let that gas, release that gas in a hurry, and you get a really cold temperature in a hurry. Okay? So if that behavior holds true no matter what you're doing.
Just like blowing like on food or something, like it be cool there.
Like just blowing air on something, that's usually a little bit different process. When you're blowing like air, you get a breeze that makes it cooler in the summertime. That really has more to do with the evaporation of the moisture on your skin than it does to do with lowering the actual temperature. It does a little bit, but almost not enough to measure. Okay, you have to have more pressure being released and things like that for that to actually happen. Okay. Okay, why don't you fill the rest of that out in pen? Okay. All right, so you have a pen, don't you?
Mm-mm.
You're required to have a pen in here. So if we do the actual math, we find that if we put volume over temperature, and we keep changing volume and temperature, and measuring, and then multiply, and then doing the division here, dividing these, you find that this is going to equal a constant. Like yesterday, when we multiplied our pressure and volume together, and we did all those pressures and volumes and multiplied them together, we got the same number every time. Well, if we take the volume and temperature and we divide, no matter what we change volume and temperature to be, as long as we keep the other conditions the same, we get that constant like we did with Boyle's law constant this way. So we call this an inverse relationship, where when the volume was increased, the pressure decreased. Well, in this case, then, volume is always going up when temperature goes up and vice versa. Okay? But you always get it equal to a K. This is a direct relationship. Yesterday was inverse. Okay? Yesterday was an inverse relationship. Today is a direct relationship. Okay?
Was it inverse because, like, when the volume of gas went down, like, the pressure increased?
Yeah. Yeah, that's why it's called inverse. And so the graph you saw yesterday was the result of an inverse relationship. Okay, from Unit 1, you're supposed to be able to recognize graphs that have an inverse relationship and a graph that has a direct relationship. So when you have a direct relationship, you have a positive slope, a straight line with a positive slope, which is a direct relationship. Okay? All right, so if this is true, then if I change the volume, then the temperature is going to change with it, so that we always are going to be equaling a K. Okay? Whatever you change it to. So if I have a beginning volume and a beginning temperature, and an ending volume and an ending temperature, they're always equal to K. Which means that these two are equal. And this gives us then the most practical form of this equation for solving problems. Okay? So the basic idea behind Charles' law is just this relationship right here, V over T equals K. But when we do a little bit of math manipulation here, we see that we get this, which is much more practical for solving problems. So this is one of those things like yesterday, when we had Boyle's law, if you have 3 variables, you can solve for the 4th. Same thing here. If we have 3 variables, we can solve for the 4th. Okay? No. Alright, you're going to use the same steps to solve this problem. Okay? List your knowns and unknowns. Write your equation that fits those knowns and unknowns. Plug in the known values. Cancel units. Isolate the unknown. Solve the problem. Okay? So you should have everything you need now to solve this problem. You've been doing this sort of math for years. So solve this problem now. Make your list of knowns and unknowns. You may work with somebody close to you as long as you do so quietly.
Is the list of knowns and unknowns the same except you're using two? Like,
Well, you just go through and say, okay, what dimension of measurement is this measuring?
yeah.
Volume.
Volume. What dimension of measurement is this measuring?
Oh.
T for temperature. What about this one?
Same thing.
Okay. So you make the list the same way we did before. Okay?